Johnny here with Simpson Math. In this video, I want to quickly run through the curve sketching checklist from start to finish to give a sketch of this function f, which is defined as x times e to the x. So I want to know, what does this function look like? And to start off with any function, you really should start off with the domain. What can I plug into the function? And what can I not plug into the function? So domain, well, the first factor is just linear, that's fine. The second factor is exponential, which is famous for being unrestricted. So I can plug in negative numbers, zeros, positive numbers, fractions, irrational numbers. They seem to be all fine. So all real numbers is the domain of this function. All right, since I talked about domain, it might be wise to talk about vertical asymptotes next. Vertical asymptotes will only occur at points of discontinuity, or like domain restrictions, basically, and then maybe end points of a function. Like if for some reason I'm bounded by 2, then I may have a vertical asymptote at 2. But this function has no domain restrictions, and it's going to stretch left and right forever. So I can already tell there's no vertical asymptotes. And I can tell that, again, because there's no domain restrictions, and then there's no stopping spot on the function. Now, horizontal asymptotes, that's a different story. If I want to talk about horizontal asymptotes, that's the end behavior. So the very right tail of this function, I want to know, am I approaching a number, or maybe I'm skyrocketing up to infinity. To find that out, I'm going to evaluate the limit as x approaches infinity. To evaluate the limit, I'm going to try direct substitution. I get infinity times e to the infinite power, which is still infinity. So yeah, that's really going up to infinity. Oh, so that's not a horizontal asymptote behavior. That is rising on the right behavior. As x goes bigger and bigger, so does the function. I now know that this function is rising on the right. Now that's the right tail. I'd like to know about the left tail. So I'm going to evaluate the limit as x approaches negative infinity. Wait, it's an x. And let's see, I can kind of see what's going on. Let's just try direct substitution. Infinity times e to the negative infinity, which that's just going to go ahead and rewrite it as a ratio. I'm going to put that e to the infinite power down below. Oh, that's a negative infinity. So I'm getting negative infinity over infinity, which is one of those ratio indeterminates. Not quite sure what's going on here. So I'm going to apply L'Hopital's rule. Now, I got the ratio indeterminate because I took my product and I rewrote it as a ratio. So let me clean that up real quick. I said this function is equal to another function where I rewrote e to the x as 1 over e to the negative x. And this is when I direct substituted and I got the negative infinity over infinity. For L'Hopital's rule to apply, I have to get a ratio indeterminate. And so I wanted to show that this is where that came from. Not the product, but from that ratio. Okay, if I get a ratio indeterminate like that, I can apply L'Hopital's rule. So here we go. I'm evaluating the same limit as x approaches negative infinity, but I'm going to take the derivative of the numerator separate from the denominator. The derivative of 1x is 1, and the derivative of e to the negative x will be a negative e to the negative x. Now if I try direct substitution, I get 1 over negative e to the negative infinity. Okay, well that's now positive infinity. So I get 1 over negative e to the infinite power. Okay, well, that's a really big negative number. So that tells me I'm getting negative 1 over 0, which is, negative 1 over infinity, which is going to 0, but that negative kind of clues me in that I'm approaching 0 from below, from the negative region. So I'm going to go through my negative signs and make sure I did that correctly. Plugged in a negative, which became positive up there, but this is still negative on the outside, still negative on the outside. So I'm going to put little arrows here that tell me this is going to 0. I'm going to put a minus sign there, which is nonsense. You can't have negative 0, but I'm approaching 0 from the negative region. Interesting. So there is a horizontal asymptote at y equals 0. So because the limit as x approached infinity was a number, I have a horizontal asymptote at y equals, and it's going to 0. So with that information, I can give you maybe a rough sketch. If here's 0, as I go left, I'll be approaching 0, but from below. And then on the far right end, I'm going up. So something like this. Maybe I turn around. I mean, I'm going to have to do something here. I'm assuming it's something like that. Because I'm rising on the right, and I'm approaching 0 on the left from the negative region. Okay. Oh, I've got some check marks. I did the domain, all real numbers. Because of that, the vertical asymptotes were easy. There were none. And then I just found the end behavior using the horizontal asymptotes. So now I'm rising on the right, and I have a horizontal asymptote at y equals 0. All right, next on my checklist is to talk about a change in behavior, change in increasing and decreasing behavior. So to do that, I'm going to need the first derivative. I can go off and find that. F prime of x. Well, I'm just finding the derivative of a product. So I go first, d second, plus second, d first. Clean this up a bit. I can factor out an e to the x, and then I have another factor of x plus 1. Now, I'm supposed to take a look at the domain again. If I have any sort of new domain restriction, that will be a critical value and an opportunity for the increasing and decreasing behavior to change. So, domain. Exponentials, still good. Linear, still good. I'm good. All real numbers, no critical values yet. I'm going to continue. Critical values on the first derivative can also occur at the roots. So I'm going to set the first derivative equal to 0. Well, because I factored, I can now set each factor equal to 0. And solve them independently. Now the first one will never happen. If I plug in negative numbers, I get a small number. If I plug in 0, I get 1. If I plug in a big number, I just get a big number. I'm just going to discard this. Exponentials are famous for their shape, and without a vertical shift, that thing will never touch 0. Now here, x equals negative 1. Here I have one critical value. If there is behavior change from increasing to decreasing, it'll happen here. So in order to determine if I do have that change, I'm going to do a number line summary. I'm going to test a number less than negative 1 and greater than negative 1. How about 0 for a number bigger and negative 2 for a number smaller. I'm testing the first derivative. F prime at negative 2 will be e to the negative second power times negative 2 plus 1. I'm just plugging negative 2 into my first derivative. I'm looking for if it's positive or negative in the end. Well, like I said earlier, e to a negative number is just a small number. This is 1 over e squared, and this is negative 1. Negative 1 times a positive number, this is going to be a negative. And where f prime is negative, my original function f must have been decreasing. I'm going to test 0 real quick. F prime of 0, well, that should be easy. E to the 0 times 0 plus 1. 1 times 1 is a positive 1. So where the first derivative is positive, the original function was increasing. So I do have a extrema, a point where decreasing behavior changes to increasing behavior. So I was decreasing to negative 1, and then I was increasing from here on out. So I do have this local minimum. Turnaround point. I can go off and find that local minimum. Let's see, with increasing, decreasing behavior, maybe I'd like to talk about the intervals of increasing and decreasing before I continue. So f, the original function, is increasing from negative 1 to infinity and decreasing from negative infinity to negative 1. Okay, this actually makes a lot of sense with my previous sketch. I start off decreasing. If I'm going to be approaching 0 from the negatives, I have to do it like this. So if I read it left to right, yes, I'm decreasing. And then I get to a point, clearly at negative 1, where that decreasing behavior changes, and now I am increasing. Something like that. I went from decreasing to increasing, and I have some sort of local maximum, or local minimum, sorry. In fact, because of how this graph is represented, with its, like it's always increasing to the left, always rising to the right, there's no other end point, there's no other low point, I can tell this is going to be a global minimum or an absolute minimum. That's another story, maybe. Okay, let's go ahead now and find the local minimum. I'm going to check off, though, that we know the increasing and decreasing behavior. We have those intervals, 2 intervals. Now, the local min, I want the actual point where I change in behavior. So I'm going to plug that negative 1 back into the original function, f prime. I'm sorry, f. Let me try that again. Green pen's not doing too good. I'd like to find that local min. That's f evaluated at negative 1. So I have negative 1 times e to the negative first power. Original function, plug in negative 1. Well, that's just negative 1 over e. Oh, so I have a local min at neg 1 comma neg 1 over e. If you're graphing that and you want a decimal approximation, e is about 2.7, so that's roughly about a negative third, but that's all I needed right there. Negative 1 comma negative 1 over e. Got it. right, I'm pretty happy with my sketch. So clearly this point has a y value of -1 over e. I put the x-axis here because it's to the right of -1. So I think my graph is fleshing out, looking nice. Now, I would like to know next about concavity. This is concave down, and if I'm rising over here, oh, maybe I'm not sure that my concavity changes. I could do something weird. Like, I don't know, something like that, but it has to go up. Yeah, I think there's probably a change in concavity. So let's go off and find out if there is and where so. To do that, we look at the second derivative. So my first derivative is e to the x times x plus 1. So the second derivative will be another product rule. First, d second plus second d first. Looks like I can factor e to the x out again, leaving me with, I could have added, I guess, but that's 1 plus x plus 1. I'll just call that x plus 2. If there is a change in concavity, it should occur at, I guess, new domain restrictions and roots of the second derivative. Domain is totally cool here. So I'm just going to find the roots of this second derivative. This is very familiar. We did the exact same thing just above. Because I factored, I can set each factor equal to 0. This is nonsense here. It's never going to happen. Here, though, I get x equals -2. This is the only place that concavity may change. To determine whether it does or not, I'm going to create a number line summary where I put that critical value on a number line. I'm going to test a value bigger, like 0, smaller, like -3. I'm testing the second derivative. Just really concerned with if it's positive or negative. So e to the -3rd power is a positive 1 over e cubed. And then this is -1, so this is negative. And where the second derivative is negative, the original function is concave down. I am definitely concave down from -infinity to -2. I have not determined yet if there is a change. So I'm going to test 0, a number bigger than -2. Ah, 1 times 2 is 2, which is positive. Where the second derivative is positive, the original function is concave up. There is change in concavity. Before I move past concavity, I'm going to go ahead and mention the intervals of concavity. F is concave down over the interval -infinity to -2, and concave up from -2 to infinity. Definitely an inflection point when x equals -2. To find that inflection point, I'm going to plug -2 back into the original function. Evaluating my original function at 2. My original function is that. 2 times e to the 2. So 2 times e squared. Doesn't make any sense to me. Because did I do that right? Oh, -2. That's what it is. -2. -2. -2. -2. -2. -2. Gross. Sorry. All right. With the -2, an exponent, I can just reciprocate to get 1 over e squared. So I have -2 over e squared. That's what I was thinking it should be. So there we go. I have an inflection point at -2, comma, -2 over e squared. Decimal approximation, e squared is about 7.427-ish. It's good enough. All right, let's see. So on my graph, at -2, and it would be smaller, 1 over e is about 1/3, 2/7 is smaller. I'm going to have a change. I'm going to draw this in a second. This is -2 over e squared, about -2/7-ish. This is where I have a change in concavity. I go from being concave down to being concave up. All right. I've got the basic shape. It would be nice if there were a y-intercept, which there is one. I'd like to know where that is. There's definitely an x-intercept. I'd like to know where that is. So before I graph it, I'm going to go ahead and get the intercepts. It's not on my checklist, but oh wait, it is. Really weird, sorry. Yeah, I would like to find the x-intercepts. And I'm going to go ahead and add to this list. Let's get that y-intercept as well. This is old school algebra. If you want to find an x-intercept, you set the y to 0. I've done this 3 times now. It feels like it's already factored, so I can set each factor to 0. I can discard that one. So I have an x-intercept at 0, 0. This answers my y-intercept question. I just said I'm going to have a y-intercept. And of course, you can only have one if it's a function. And there it is right there. Going through the motions. To find the y-intercept, you set the x's to 0. So yeah, 0 times 1, you get 0. Cool. I think I can graph this function now. I have a point at 0, 0. It's acting as not only my x-intercept, but also my y-intercept. I know the end behavior on the right. It's going to rise to infinity. I know my end behavior on the left. It's going to approach 0. It starts off decreasing. It starts off concave down. At some point, the concavity changes. At some point, I turn around, and then I'm increasing forever. So there's a point of inflection, and then there's a global minimum. And that should be more curvy evident. I have a point of inflection at -2, comma, -2 over e squared, a point like a local minimum, also acting as my global minimum at -1, comma, -1 over e. I've got this asymptote at y equals 0. Horizontal. So this is just using calculus to talk about end behavior, change in behavior from increasing, decreasing, and concavity, change in concavity, to get a nice sketch of the function. And of course, I highly recommend you plug that into desmos.com or some sort of technology just to verify that what you're getting on paper makes sense. All right, continue curve sketching, and I'll see you in the next video.